Hello everyone, welcome to our differential equation class. In this video we are going to talk about phase portraits of solutions to 2x2 systems of differential equations. First we are going to focus on the equation itself, and we are going to see that the equation determines something that is called a direction field. After that we are going to focus on the solutions of the system of equations, and we are going to see that the solutions can be graphically represented by curves on an appropriate plane, and a phase portrait is nothing more than this solutions curve graph for different values of the initial condition. So several solution curves construct a phase portrait. In the rest of this video we are going to construct a phase portrait for solutions of 2x2 system of linear differential equations in the case that the differential equation, the matrix in the differential equations has either complex eigenvalues or real eigenvalues. To do these graphs, it's important that we review a little bit what are the solutions formulas we are going to use to actually graph these solution curves. So that's the plan for this video. Okay, let's start with a few definitions, and our first definition is the vector field of a system of differential equations. So consider a system of differential equations like this one, which is a 2x2 system of linear differential equations, and the vector field of this equation is defined by only the right hand side of the equation. So the vector field is this with the right hand side of the equation. This is a function, is a vector value function that for every vector x, the matrix vector product gives you a new vector that we call f. So the right hand side of the equation defines a vector value function that is a vector field. Now the direction field associated to the equation is nothing more than a normalized version of this vector field. That is, the direction field of this equation is a unit vector field given by this function f divided by its own length. So at every point we have the vector f, we divide by its own length, and we get a new vector pointing in the same direction as f, but the new vector is a vector that always have length 1, a unit vector field. That is the direction field. Then we introduce one more concept, which is the solution curve of this equation, which is a curve given by the component x1 and x2, where x1 and x2 are the components of a solution of the differential equation. So recall that in the case that the matrix A is constant and we have a diagonalizable matrix, then we have solution formulas for the solution of these equations in the case of complex or real different eigenvalues. And so we have formulas for these components. Well, these components define a vector in the appropriate solution space, and the endpoint of the solution vector, we collect all these endpoints, and that is what we call a solution curve. So let's do a little pictures to get all these ideas in a more clear way. So all these graphical representations are on the plane x2, x1, where x1 and x2 are the components of the solution. So the plane x1, x2 is what we call the phase space, this plane here, where we are going to plot all these solutions. Suppose we have a solution vector with component x1, x2, solution of the original differential equation. Suppose at a particular value of time, this is the solution vector. Okay, so this is how we are going to denote the solution vector, or we can also use the column notation x1 of t that we have been using up to now. Column vector, or a vector with brackets. The endpoint of this vector is going to be denoted with a pointer notation, and it has exactly the same components as the vector, of course, but we are focusing only on the endpoint, so we use parentheses instead of brackets to denote only the endpoint. Now, when you put the solution formulas here for the components, well, here if you put the solution formulas, we are going to get different points for different values of the time variable. So that is what later on that is what we have called a solution curve. A solution curve is going to be the endpoint of solution vectors for different values of the time variable. So this is the solution curve. All this is represented in the phase space. So let's keep going with the remarks. Our next remark is just to fix ideas. Suppose you have a vector, a solution vector that at one particular time has component 4, 3, for example. So let's recall that the magnitude or the length of this vector, what we denoted here with these double bars up here, given a vector, this is nothing more than the square root of the component of the vector square add up. So this is the length of a vector. This is the notation we are using up here. Then, what is a unit vector now? Well, a unit vector in the direction of this vector v is nothing more than the vector divided by its own length. Well, but if the vector is the vector, for example, 4, 3, and the length is 5, in this case it's going to be 16 plus 9, 25, square root is 5. So what the unit vector here is nothing more than the vector divided by the length, which is a vector with components 4/5 and 3/5. This vector now is a vector in the same direction as the original vector, but because we are rescaling with the length, this vector, if you compute the length, is going to have length 1. Length 1. So if we do a little picture, this is what we are talking about. We had an original vector, and now we rescaled the vector to be a vector of length 1. So this is the main difference between a vector field and a direction field. The direction field is the same as the vector field, but every vector has now length 1. This is what we were saying up there. So to understand now the concept of a vector field, which is a review because you should have seen it in Calculus 3, a vector field is a vector at each point x on the phase space. So at each point here we have a vector pointing in maybe different directions. So for example, suppose that we have a matrix that is the matrix 3 minus 1 2 1, to say something, and our variable vector is the vector x1 x2. So now what is this function f of x equal the matrix acting on the vector? Well, we need to do this product, and this product here, the matrix vector product, and if we do that, what we get is a vector field that in the bracket notation looks like that. So you see for any values of x1 and x2, we need to do the product, and we get 3x1 negative x2, that is right there, and then this product here, and then we get 2x1 plus x2. In in the column notation is what we've been using up to now, and in the bracket notation is what we have here. Now this is a function, so you see you give me x1 and x2, and then I get here a vector. And we can do that for every value of x1 and x2. So let's see how this vector looks like, for example, at one particular point. So let's graph only this vector field, but only at one point in the phase space, the point 1, 1. Okay, let's do that so we have an idea what we are talking about. Solution. What we need to do is we need to compute the vector field at the point 1, 1. So this is the origin point of the vector. We will see in a minute. And what happens when we put x equal 1 and x1 and x2 equal 1? So we are going to have here 3 minus 1 and then 2 plus 1. So this is the vector with component 2, 1. So these are the vector components. So if we graph that, what we need to do is we need to do the vector with component 2, 1. But so 2, 1. So we would say, oh, is this vector here? 2, 1. What did I say? 2, 3. Sorry. 2 plus 1 is 3 the last time I checked. So let's put here 3. 2, 3. Okay. So now let's graph that. So we have to graph a vector with component 2 and component 3, isn't it? Well, this is the vector, that's correct. But the vector has to be, the origin of the vector is this point, is not the point 0, 0. So actually, in a vector field, you need to draw the vector at each point where you compute the vector. In this case, at 1, 1. So here we need to go to the point 1, 1, which is here, the point 1, 1. And then we need to draw the vector which has two components. This component has component up to here 2 horizontal, and vertical is 3 components vertical up to here. This is 3. So this is the vector that we should be plotting. This is the vector f at the point 1, 1. So this is a vector field. So this is one point in the vector field. Suppose you grab the point 1, 2. Okay, you compute what is the new vector. So at 1, 2 here, there you plot what is going to be the vector at there. And then you do it at 3, 1. So you go to 3 and 1, and here you plot what is the other vector. And then you're going to have a vector on each point on the plane, and that is a vector field. Let's see an example of a vector field with a little bit more physical meaning. So draw the vector field of a system of first-order differential equation given by a mass spring system oscillating without friction. So we have this system, the usual spring with spring constant equal 1, mass equal 1, no friction, oscillating back and forth. Our variable is y. And what is the vector field of that? Okay, so let's recall first what is the system of equation that this system satisfies. In general, is Newton equations. And here we have the equation is mass times the acceleration plus the friction constant d times the velocity plus the spring constant k times the displacement equals 0. And in our case, we have mass equal 1, d equals 0, and constant k equal 1, so pretty simple system. So that is gonna say that the equation we need to solve is a second order equation, y double prime plus y equals 0. Well, this equation is a second order linear differential equation. To talk about the vector field of this system, we need to write this equation as, so the second order linear differential equation has to be written as a system of, well, as a 2 by 2 system of first order linear differential equations, because we have defined the vector field here. So we need to do the first order reduction. How we are going to do the reduction? In the usual way, we are going to call x1 of t to be the function on the problem, in this case the displacement, and then x2 of t is the derivative of the displacement, so the velocity. With that, we get one equation that is fixed by this definition, which is that x1 prime is equal x2. Okay, what is the equation for x2? Well, x2 prime is y prime prime, so double prime. But from here, we see that y double prime is negative y. But we just said that y is x1. So this is negative x1. So the system of equations is x2 prime equal negative x1. So this is our system. So now let's go to the vector form of the system, x prime vector, and this is, well, this is x1 prime, x2 prime. But we just said that x1 prime is x2 and x2 prime is negative x1. So that is the system of equation, and we can write it down in a more usual way as a matrix acting on the vector x1, x2. If we want to, we don't have to, but we can. And this product has to be equal x2 only. So that means we have here a 1 and a 0. And then this product has to be equal negative x1, which means we have a negative 1 and a 0. So our matrix A, so this is of the form A, x, and our matrix A is, well, 0, 1, negative 1, 0. Anyway, what is the vector field here? Well, the vector field is here. So, or what is the same here? It's the same. So our vector field for the mass spring system at the point x1, x2 is gonna be ax, but you see ax is 0, 1, negative 1, 0. I am redoing what I did. And then we get the vector x2 negative x1. So we can say like this. So the f in the column notation, column vector notation, is just x2 negative x1. But now I'm going to use the bracket notation to write down the same vector, which actually is a vector field. So it's going to be x2 negative x1. So you see, this is a vector field. At every point we associate this vector. Okay. So here we have the origin point, and here we have the horizontal component of the vector and the vertical components of the vector field. Okay. So here we are going to plot that vector field for several values of the variable in this little picture, and we're going to make it a little bit higher up here. Okay. So let's start giving some points. For example, what happens when we put the point 0, 0? Well, we get the vector 0, 0. So that we represent that by saying here that we have just the vector 0 in our vector field. Okay. What else? Well, let's go to the point 1, 0. So we are here. So at this point, where is the vector here at this point? At the vector there, at that point. Well, what we need to do is this vector, this component goes here as a -1, and the component 0, x2, goes on the front. So we flip the order and we reverse the sign on the second component, but here is like that. So this is a vector. This is a vector at this point, and notice that this vector is a vector that has 0 horizontal component and vertical component -1. So this is a vector like this. But here, so we are talking about 0 horizontal component, 1 vertical component. So that is that vector at the point 1, 0. Okay. So let's continue. Let's give another point. So let's go to the point 1, 1. So what is the vector field at the point 1, 1? Well, it's gonna be this one goes. This is the one that goes on the back with a negative sign, and this one goes in the front. So we are gonna have 1, -1. So that is a vector with components 1 horizontal and -1. So 1 horizontal and -1. So it's a vector like this. And this is at the point 1, 1. So what is the point 1, 1? Is here. The point 1, 1 is right there. And then it has component 1 positive and then 1 negative. So it's this vector here. So it's a vector like this, more or less. That's interesting. Then let's keep going. F at which point now? What about if we do it at the point 0, 1? Okay, so x1 is 0 now, so that is 0, and x2 is 1. So this is a vector that has horizontal components only, and it's at the point 0, 1. So it's at the point 0, 1. Recall that our convention, this is x1, this is x2, this is the horizontal component, this is the vertical component. So 0, 1, at this point, we have a horizontal vector. So at this point here, we have a horizontal vector with components 1, 0. Okay, let's do a couple more, and then I give you the general picture. So let's complete the circle or the square. Let's go to the point -1, 1. So -1, 1. At which point are we talking about? So -1 horizontal, 1 vertical. So here, at that point, this point here, what do we have? Well, the vector x, that is going to be the +1 and then +1 here. So it's going to be a vector like this. But at that point, so at this point here, there. So what else? Let's do yeah, so we can keep going like this, and what we are going to end up is with if you keep giving values for x1 and x2, you're going to end up that here, for example, you're going to end up with a vector like this. Here you're going to end up with a vector like this. For example, here you're going to end up with a vector like this, and here with a vector longer like this, and here component 3 like this. What else? The same is going to happen here. We are going to have a vector like this, and here a vector with two longer like this, and here a vector with with component 3 here like this. See what is happening, and then if you complete, for example, here you're gonna get a vector like this, here a vector like this. Let's make it a little bit nicer, doesn't need to be so ugly. And we have all those, and yes, here is going to be a vector with with component 2, so it's going to be more or less like this, and here it's going to be with 3. And that is more or less what is happening, but it's much better if we get a computer to do it, because you see we need to do the graph of several vectors in several positions, but this is more or less what appears to be happening. The vectors kind of rotate around 0. And if you have a computer, you are going to end up with something like this. This is the vector field for the spring, where the components are x1 and x2. And recall, x1 and x2 have physical meaning. This is the displacement, y, and this is the velocity, y prime. We are going to go over that later in more detail, but in this plane, this is the vector field associated to the equation. And what is the direction field? So notice that the vector field is getting bigger the farther away we get from the origin, and smaller the closer we get. So if we normalize the magnitude of the vectors to 1 everywhere, we have a more clear way of what is happening. It's a rotation here. And what we are plotting here is the original vector field divided by its own magnitude. So all these vectors have length 1. So that is a vector field with some physical meaning that we are going to talk later in more detail. So this is the displacement. This is the velocity. Our last example on vector fields is matching. That this is the type of exercises, that we have in the homework. So the exercise is match each of the following vector fields or the following systems with the corresponding vector fields. This is how the vector fields looks like. And here I have some ground labels. For example, here I'm talking about x and y for the components of the function. And here x1 and x2. Well, the x1 is always x, x2 is always y. Okay, so how we do this matching? Well, actually we need to do very little calculations to figure out which vector field goes with what system. Very little work. Solution. This is to get intuition on given equations, how the vector fields of these equations looks like. And what we need to do is essentially two things. The first one is to find the zeros of the vector field. Finds the zeros of the vector field. What is that? Okay, let's grab the system in A. And the vector field associated to that system is given by the right hand side. So the vector field F at the point I'm going to use x and y here is x minus 1, y minus 1. Okay, find the zeros means find x and y such that this is 0, 0. Which is kind of simple, because the system is linear. So that means x is equal 1, y is equal 1. So that means there is one point where this vector field vanishes, and this is the point p0 equal 1, 1. Well, clearly the point 1, 1 probably is here. So here is so what I'm trying to say is where these vector fields vanish. Here, these vector fields. Well, this vector field vanishes obviously here. This vector field vanishes at 0, 0. This vector field vanishes at 0, 0, we can see from the arrows, and this one is gonna vanish here. So probably, for sure, this vector field vanishes at p0 equals 0, 0. So this cannot be A. The system A cannot be figure 1, because figure 1 vanishes at 0, 0, and this one vanishes at 1, 1. The same happens here. This p0 is 0, 0. So figure A, so the system in A cannot be this one and cannot be this one. Okay. So, but it could very well be this one, or very well be that one, because we could say here that this is 1, 1. So probably is that one, or probably is this one. I don't know which one of these two, but there are two vector fields that cannot be 1 and 3. Okay. So, well, what do we do? How we decide whether this system corresponds to this vector field or this one? We grab any other point, a simple point. For example, 0, 0. And at 0, 0, we see that we have a vector field like this at 0, 0. And this one at 0, 0 has a vector like this. So the only thing we need, and they are different. So the only thing we need to do now is to compute f at 0, 0 for the system in A, which is actually -1, -1. And this is a vector of the form -1, -1 is a vector at 0, 0, is at this point. So this is x and this is y. Is a vector of the form -1, -1, so like this. That one here, not this one. Perfect. So therefore we conclude that system A has to be the one in figure 2. That's it. With a couple of evaluations in cleverly chosen points, you can determine, given a system of equations, what is the corresponding vector field. So exercise, match the rest. Oops. Exercise. Match the rest. And after I finish the video, I'm gonna post the solutions, because the solutions are here. Okay, so that's essentially all we wanted to say about vector fields, direction fields, and of a system of differential equations. Now let's move on to phase portraits. And in order to do that, we need to review the solution formulas from previous videos. Recall that when you have a system of linear differential equations like this, constant coefficients, homogeneous, 2 by 2, in order to find solutions of this equation, we need to compute the eigenvalues and eigenvectors of the coefficient matrix A. Suppose we did that, and we have the eigenvalue lambda plus corresponding with eigenvector v plus, and lambda minus with v minus. And suppose now we have different solution formulas depending what these eigenvalues are. For example, if the eigenvalues are different and real, so A is diagonalizable, then we have fundamental solutions given by exponential eigenvalue times t multiplied by the eigenvector, and the same for the other pair. And then the general solution x of t is going to be a combination of these two solutions. That is going to be the general solution. These are fundamental solutions. And the other formula is when we have eigenvalues which are complex values. So suppose the eigenvalues, in this case, because the matrix has real coefficients, the eigenvalues are going to have this form: plus or minus IB, alpha plus or minus IB, alpha and beta, I beta. Beta and alpha are real, and here is the complex I. And the eigenvectors are going to have the same, a similar form, a real part plus minus the I plus B. And then the fundamental solutions have a slightly different form. They can be written as exponentials or as these real value functions, which are the exponential with the real part of the eigenvalue, and then the imaginary part comes in the oscillatory part of the solution that contains the eigenvector, the real part, and then the imaginary part here, multiplied by the corresponding sine or cosine of beta t. So we assume that we know these formulas very well, and now we want to try to construct what is called the phase portrait of these solutions. We are going to focus only on these solutions and that. And actually, in this video, we are going to focus on the solutions in this case. In the case that the eigenvalues are complex. This is today. But let's recall what we said at the very beginning. What is a phase portrait? A phase portrait is nothing more of a 2x2 system of differential equation. Is nothing more than the graph of several solution curves on the phase space of the system. So we choose different initial data and we graph several solution curves until we get an idea how the solution curves behave in the phase space. Recall that the phase space is what the space where we were graphing the vector field, is the space with component x1 and x2. We graph the solution. These are the values of the solution for different values of the variable t. If we start drawing arrows all the time, it's going to be super messy. So instead of drawing the whole arrow, we're going to focus only on the endpoint, no more arrows, and then each solution is going to be represented by a curve. The curve is the endpoint of the vector field that is moving. In a phase portrait, we graph several solution curves for several initial conditions, and we graph only the curves, not the whole vector. And what we want to focus today is in the case of complex eigenvalues. So we're going to sketch the phase portrait of this solution, which, by the way, is the fundamental solution that we called fundamental solution 1 before. Let's see if it's true. So is the A cosine minus B sine. A cosine minus B sine. So yes, is the solution 1. This is the solution we are going to graph. And we are going to have A and B are arbitrary vectors. We are going to choose some directions for these vectors. We are going to keep beta arbitrary, and alpha, the graph is different for different values of alpha. If alpha is positive, negative, or 0, we have different pictures. So we need to do the picture for at least one or two of these cases. So we are going to work on the phase plane. So let's do the let's solve this problem. Solution. let's put it here because we are short of space. What do we want to do? The face portrait of what? Of this. Okay, how do we start? Well, we start saying that we are going to draw the parts that are needed to do the picture, and the parts that they are needed is the vector A and the vector B. These are the most important parts. So before doing the face portrait, draw the vector A and the vector B, and also draw, because we are going to need it, the negative of the vector A and the negative of the vector B. Okay, and after that, draw these 4 vectors, determine an ellipse on the face space. Draw that ellipse. If you do all that, I'm gonna choose here vectors on, so this is gonna be x1, this is gonna be x2. I'm gonna choose two arbitrary vectors. I'm gonna choose vector A to point in that direction for no reason, and vector B to point in that direction for no reason. It's just to have a nice picture, but the problem is gonna determine what are your vectors A and B, and I'm choosing these 2 directions to do the picture. Okay, if those are my vectors, then this is the picture so far. And let's fix ideas, and suppose we are gonna work with alpha positive. So we are going to put here case 1. Case 1 is going to be alpha positive. Okay. So I've chosen some vector V just to do the A to do the picture, some vector B. Since I need to draw A and B, let's suppose are these 2 vectors. Then we need to draw the negative. So the negative of this vector is this vector here, and the negative of this vector is this vector here, and then the 4 vectors determine an ellipse. Okay, this is the preliminary work. What do we do now? Well, the next step is step 3, is start computing the solution now. Now we are gonna start working on x1, and what we need to do is compute x1 at t equals 0. So compute x1 at 0. Here at 0, t equals 0. But this is the formula for x1. What happens when we put 0 here? Exponential 0 is 1. What happens when we put 0 here? Cosine of 0 is 1. What happens when we put 0 here? Sine of 0 is 0. So all these disappear, and we end up only with A. So no matter what is that vector A, but we are going to have, let's put that in writing, exponential 0, A cosine of 0, minus B sine of 0. And recall what we said, this is 0, this is 1, this is 1. So we end up with x at 0 to always be A. No matter what are the values of the parameters in our problem, we are going to end up with this point, which is the solution 1 at 0. It's always there. Okay, good. So what do we do now? Now we compute the solution at one more point, and we are done. So we are going to compute the solution. The last part of the problem is compute x1 of t at this is the vector, at one particular point t1, and we are going to choose t1 so that this here is 0 and this here is 1. So we are going to choose t1 such that beta t1 is pi over 2. The argument inside the cosine and the sine. Of course, t1 then is given, is pi over 2 over beta. But the important thing here is that x. The first fundamental solution at that particular t1 is going to be exponential alpha at that t1. Okay, we work on that in a minute. But then we are going to have a cosine of pi over 2. Because beta t1 is pi over 2 minus b sine of pi over 2. I chose t1 to be exactly the number that does this. And then we know this is 1, this is 0. And well, the exponential is something now that we have to deal with in a minute. But we end up with the solution at this t1 is going to be proportional to the proportionality factor is this exponential, and then we are going to have negative b multiplying. So what this says is that the result is going to be in this direction, in the direction of negative b. It's going to be either here or here, I don't know exactly where, but it's going to be in this direction, here. So the solution moves from this point somewhere along this line that we need to determine. But we don't need to determine very precisely. The only thing we need to do, we need to realize is that, first of all, t1 is pi over 2 beta, isn't it? But this is positive, so the important thing for us is that t1 is positive. Okay, so then when alpha is positive, which is this case we are graphing right now, when alpha is positive, what is going to happen? Well, exponential alpha t1 is also going to be positive, but what is more important than positive is going to be larger than 1, because the exponential is going to be larger than 1. Recall, the exponential at 0 is 1, but the exponential at the positive exponent is larger than 1. So what happens here is that this implies that x1 at t1 is longer than negative b. Why? Because it's this factor multiplied by negative b, but the factor is bigger than 1. So actually we are not going to be here, we are going to be somewhere here. So let's fix ideas and let's put it more or less here. Has to be longer than negative b. And this is at t1, which is positive. So that means that the solution has to move from here all the way up to there. And it's a continuous solution. So what it has to do is move like this. Oh, well, not like that. A little bit better than that. Like this. And this is the direction of increasing time. It's a curve like that. When we keep giving values for t, what is going to happen is this part here is going to create a rotation, and this factor here an expansion. So the result is then an ellipse that goes like this. Actually, it goes like this and like this. I don't want to do the whole picture for obvious reason, but it's an ellipse that goes outside when t is positive. T is positive and getting larger. What happens when t is negative? Well, that has to come from inside. So it has to come from inside like this. But when t increases, it moves outside. So when t increases, it moves outside. This here is the region t negative. Here is the t equals 0, and here is t positive. And that is the solution x1 of t. That is the phase portrait. And the only thing we need to do this phase portrait is to graph the two vectors, a negative a, b negative b, this little ellipse, and then evaluate at 0 and at positive point. And then we know the rest, what is going to happen. It's going to be an ellipse spiraling outside. And it's spiraling outside because alpha is positive. What happens when alpha is negative? Well, all this is going to be the same up to here. Up to here is going to be exactly the same. So when alpha is negative, you need to draw a, b, negative a, negative b. Then you need to draw at t equals 0, and t equals 0 we are going to again be exactly in the same place. This is at t equals 0. The solution is going to be x1 at 0. And now we have to compute at the particular t1 that we choose to be exactly the same, so it's going to be that. But now the factor here now is when alpha enters. What happens when alpha is negative? Well, exponential alpha t1, now this here is negative number. What is the exponential of a negative number? Well, the exponential of a negative number, if you recall the graph of the exponential, let's do it here. T, and what is the exponential? Well, let's put 1 here. At 0, the exponential is 1, then increases. This is exponential t. But for negative t, it's like this, isn't it? So the exponential is always positive. First thing that we realize is the exponential is always positive because it's positive here, but it's less than 1 because it takes value here. But it's never negative. But for t negative, this is t negative, this is t positive. For t negative, the exponential is less than 1. We are here. So what we conclude is that for alpha negative, recall that t1 is positive. So the product is negative. This is positive, but less than 1. And that implies that in this case, x1 of t1 is shorter than negative b. Shorter than negative b means somewhere here. That means that the solution goes from the ellipse into inside the ellipse in that direction, and this is t positive. T positive is here inside now, and then that means we are going towards the center. So when t increases, now the ellipse is spiraling towards the origin. And when t is negative, well, everything reverses and it comes from outside. So this here is now t negative. The solution spirals towards the origin, the solution crosses at t equals 0, and then t positive, we are inside. And this is how the phase portrait of these two cases looks like. What happens when alpha is 0? When alpha is 0, well, is the simplest of all cases. Alpha equals 0, then exponential of alpha t1 is exponential 0, which is 1, and then x1 at t1 is actually equal negative b. So at alpha equals 0, we are going to be exactly here, and then we don't move from the ellipse. So the case alpha equals 0, we always move on the ellipse, and we never go away. So this is the case alpha equals 0. So let's see here, let's put it in words because I don't have a picture for that, but alpha equals 0, then the ellipse is the phase portrait. Then the ellipse is the solution curve. And notice that the direction is always the direction is always direction of rotation in all three cases is always from A, that is the solution at 0, to in the positive direction to negative B, which for these choices of A and B, it means clockwise. For different choices, it can mean counterclockwise. We are going to see that in the next class. So repeat this construction as an exercise for the second fundamental solution, for the solution x2 that has A sine plus B cosine, and you're going to see that, we are going to comment in next class or in next video what is happening in this case. And also in the next video, we are going to see, once you have this phase portrait already done on paper, how you can solve the homework problems associated to this section, which is essentially draw the phase portrait, which is what we did here. And then once the phase portrait is done, it's very easy. So once this part is done, this is the exercise, this is the solution we just have drawn, then it's very easy to answer these questions. We are going to do all that in the next video. So I think this is enough for today. Let's stop here. See you in the next video.